Which of the following functions are continuous at x equals 3? Well, as we said in the previous video, in the previous example, in order to be continuous at a point, you at least have to be defined at that point. We saw our definition of continuity. F is continuous at a if and only if the limit of f as x approaches a is equal to f of a. So over here in this case, we could say that a function is continuous at x equals 3. So f is continuous at x equals 3 if and only if the limit as x approaches 3 of f of x is equal to f of 3. Now let's look at this first function right over here, natural log of x minus 3. Well, try to evaluate, and it's not f now, it's g. Try to evaluate g of 3. G of 3, let me write it here. G of 3 is equal to the natural log of 0, 3 minus 3. This is not defined. You can't raise e to any power to get to 0. You try to go to, you could say negative infinity, but this is not defined. And so if this isn't even defined at x equals 3, there's no way that it's going to be continuous at x equals 3. So we could rule this one out. Now, f of x is equal to e to the x minus 3. Well, this is just a shifted over version of e to the x. This is defined for all real numbers. And as we saw in the previous example, it's reasonable to say it's continuous for all real numbers. And you could even do this little test here. The limit of e to the x minus 3 as x approaches 3, well, that is going to be e to the 3 minus 3, or e to the 0, or 1. And so f is the only one that is continuous. And once again, it's good to think about what's going on here visually, if you like. Both of these are, you could think of them, this is a shifted over version of ln of x. This is a shifted over version of e to the x. And so if we like, we could draw ourselves some axes. So that's our y-axis. This is our x-axis. And actually, let me draw some points here. So that's 1. That is 1. That is, let's see, 2, 3, 2, and 3. And let's see, I said these are shifted over versions. So actually, this is maybe not the best way to draw it. So let me draw it. This is 1, 2, 3, 4, 5, and 6. And on this axis, I won't make them on the same scale. Let's say this is 1, 2, 3. I'm going to draw 1, 2, 3. I'm going to draw a dotted line right over here. So g of x, ln of x minus 3 is going to look something like this. If you put 3 in it, it's not defined. If you put 4 in it, ln of 4, well, ln of 4 minus 1. So that's going to be ln of 4 minus 3 is, actually, let me just draw a table here. I know I'm confusing you. So if I say x, and I say g of x, so at 3, you're undefined. At 4, this is ln of 1, which is equal to 0. So it's right over there. So g of x is going to look something like that. And so you can see at 3, you have this discontinuity there. It's not even defined to the left of 3. Now f of x is a little bit more straightforward. If you have, so e to the 3 is going to be, f of 3 is going to be e to the 3 minus 3, or e to the 0. So it's going to be 1. So it's going to look something like this. It's going to look something like that. There's no jumps. There's no gaps. It is going to be continuous at, frankly, all real numbers. So for sure, it's going to be continuous at 3.